Now, what if we want to do confidence intervals for quantitative data? So far we've just looked at categorical data, but what if the data is going to be quantitative, meaning that we're going to be trying to estimate the population parameter mu? Well, every single confidence interval in the world has the same format. It's estimate plus or minus margin of error. The estimate or point estimate depends on what kind of problem it is that we're doing. So you can see our next formula looks very similar to the previous formula that we were using, but now we're looking at quantitative data. So to construct a confidence interval for a population mean mu, well, what is the unbiased estimator of mu? Oh, that's x bar. What is the standard deviation of x bar? That's S of x. Okay. Notice we have a new critical value. We have this T star, but T star here, which before we looked at Z star, now we're going to look at T star. Okay. Basically, it's the same thing. It's the number of standard deviations you are away from the mean. And that number of standard deviations away from the mean is determined by the confidence level. Remember, 95% is approximately 2, and so on. We saw that if we want to be 90%, it was about 1.645, and so on. So that table will give us the answer. Now, that's if the data is perfectly normal in the perfect world where we can use z-scores. Now, we're going to take a look at this t interval. We're going to talk about t having degrees of freedom. Okay, there's always n minus 1 degrees of freedom. So as n gets larger and larger, these t star curves or these t distributions will start to get closer and closer to the normal curve z distribution. So you can tell that these t curves have much more area out in the tail. There's more air involved in these because we don't have that perfect normality situation. The data certainly looks symmetrical. Absolutely does. However, since there's more area out here in these tails as n gets smaller and smaller, we're going to need another way to find those critical values or those star values in order to calculate our intervals. So let's say I want to do a problem where n equals 6. Well, that means that my degrees of freedom would be 5. And I want to be 95% confident. So I'm going to have to come over here to this table again, table B, and I'm going to find 5 degrees of freedom. So 5 degrees of freedom, and I want to be 95% confident. So I go across at the 5% and down to the 95%. Oh, 95 and 5. My T star or my critical value would be 2.571 standard deviations away from the mean. We're going to have to use that table every time for these T stars, or we can use the calculator. Darn it, that's what I should have showed you earlier on this previous problem. We'll look at using the calculator for quantitative data, and maybe later I'll go throw in at the end how to use the calculator for categorical data. All right, so I know from looking at the table now that the T star at n equals 6 at 95% confidence level was 2.571. So all I'm doing here is looking this up in the table. Okay. And every single value I can get that way from the table, except for what if it's not on the table? So for example, n equals, let's say n equals 75, and I want to be 98% confident. Well, if I look at my table, whoopsies, okay, 75 is not here. So in this case, my degrees of freedom is always n minus 1. So I have 74 degrees of freedom, which is what I need to use this table. Okay. So, but if we look at the table, there is no 74 degrees of freedom. We will always use the next smallest value on the table. So the next smallest value less than 75 would be 60. So I'd have to come here to 60 degrees of freedom, and I'd have to go across to 98%, and that gives me 2.39. So my critical value, T star, would be 2.39. I did it again and tried to write before I move this out of the way. All right. So that's how we use table B to find our critical value T star. Now, just like in any confidence interval, the four-step process is the same. What are we going to do? Are we allowed to do it? Do it, and then tell us what the heck it means that we just did. So now if we're looking at quantitative data, where we're going to try to find confidence intervals for X bar, we have three conditions to check. Is it an SRS? The only way to do it, did they tell us or not? Just like before. 10%, so independence. Is the population at least 10 times the size of the sample? That's the same as before. Okay? Normality is very different for quantitative rather than categorical, however. In categorical data to check normality, we did n times p hat and n times 1 minus p hat were both greater than or equal to 10. However, for quantitative data, for X bar intervals, we can use the central limit theorem. They tell us the data is normal. If n's not larger than 30 and they don't tell us the data is normal, then we're going to have to make a graph. We're going to have to, usually we'll make a box plot. If it's roughly symmetrical, so the book says if there is no strong skewness or outliers, then we're going to say it's approximately normal and we can proceed. So again, how do I check normality for quantitative data? They tell us. Central limit theorem applies, or make graph, probably box plot. Okay. If no strong skewness or outliers, then we're okay. So we have to check SRS independence normality, SRS independence normality for every single problem. Just get used to it. We got to do that over and over and over and over again. Now we're using T star again instead of Z star. No problem. We have a table to look up T star. Okay. T star is totally reliant upon degrees of freedom. There are always n minus 1 degrees of freedom. Well, let's look at an example of this. All right. In the previous section, you learned that 73% of Americans, well, we didn't talk about that, did we? Okay, let's say that 73% of American adults claim they have read a book within the last 12 months. This was based on a 2016 research study that interviewed a SRS of 1,520 adults. The same study also reported that the average number of books read by the members of the sample, including those who reported reading 0 books, was X bar equals 12 with a standard deviation sigma of 18. So we're going to construct and interpret a 95% confidence interval for the mean number of books read by all Americans in the previous 12 months. Okay. So let's work through this. We need to figure out what are we going to try to do? So remember, step 1, we want to be 95% confident of what? Okay, so we are going to be trying to measure mu. In this case, what is mu? The true mean number of books read by all American adults in the last 12 months. Okay, so always step one, define the parameter. What are we trying to estimate? You're always going to give an example, or you're always going to give a sentence about what's mu or what's p. Always, always, always. Step one, define the parameter. What are we doing? Okay. Step two, what kind of test or what kind of interval do we want to do? We are going to do a one sample t interval. Is it okay to do this interval? Well, remember, 3 steps. Okay. So check conditions. Is it okay for us to do this? All right. So the first condition, is it an SRS? They tell us random sample. So SRS, they tell us. Okay. Independence. There are more than 15,200 adults. Yeah, we're safe there. There's certainly more than 15,200 adults. Where did we get that? Population must be at least 10 times the size of the sample. So I took the sample size 1520 times 10. Yeah, definitely there are more than 15,200 adults in the United States. Normality. Absolutely. Data is approximately normal because n is greater than or equal to 30. Yeah, in this case, n was 1,520, far greater than 30. So therefore, by the central limit theorem, the data is approximately normal. So what are we going to do? We're going to try to estimate the true mean number of books all American adults have read in the last year. Are we allowed to do it? SRS, yep. Independence, yeah. Normality, yep. Yep. We're good. Whew. Now let's do it. Let's look at this confidence interval here. Okay, so we want to be, this problem is going to have lots of degrees of freedom. Okay, this problem is going to have 1,519 degrees of freedom. Remember that it's always x bar plus or minus t star times s over root n. So x bar in this case is the sample mean. 12. So for step 3, find the interval. 12 plus or minus, what is the t star value for 1,519 degrees of freedom at 95%? Well, 1,519 is not on here. So we go to the next smallest value, which is 1,000. We go across to 95% and we see it's 1.962. So our critical value, our t star, is 1.962 times our standard deviation, which is given to us in the problem here of 18, divided by the square root of n, which is 1520. We get out our handy dandy calculator, we have it do the work for us, and we'll see that the interval is between 11.09 and 12.91. Okay, so step 1, what are we going to find out? Step 2, are we allowed to? Step 3, do it. Step 4, interpret in context. So, yeah, I am 95% confident that the true mean number of books read in the last year for all U.S. adults is between 11.09 and 12.91. I'm 95% confident that that's the true number of books read per year on average for all American adults. So I can say that on average, somewhere between roughly 11 and 13 books per adult per year have been read in the United States. Let's look at using the calculator to do this for us. Okay? We want to construct a one sample T interval. So if we go into our favorite button in this calculator that says stat, calc, it's not in here. That's because now we're not calculating something anymore. We're doing tests. So we're going to go to a T interval. This is a one sample T interval. The calculator doesn't say that. It just says T interval. So one sample is the same as T. Okay? So we want T interval. Now the calculator is going to prompt us. Do we have data? Nope. We don't have all 1,520 data points in a list. So we have statistics. So we tell the calculator, we got stats. And they say, okay, cool. What's your sample mean X bar? Oh, my sample mean X bar was 12. Oh, what was your sample standard deviation S? Oh, they told me it was 18. What was N? Oh, remember N was really big. N was 1,520. And how confident do I want to be? 95%. And then I tell the calculator, do it. And it says, 11.094 to 12.096. Yeah, well, that's the same values that we calculated down here, right? We figured that out, 11.09, 12.9. Yeah, so the calculator can do all the work for us. However, it cannot do the 4 steps. It can't tell us what we're going to do. It can't check conditions. It can do calculations, step 3, but it can't interpret. So it can do the calculations, all this work here for us, but the other part has to come from you. So the calculator will do this for us. Since I messed up earlier, let's take a look at doing a one prop Z test. So let's go back on the calculator. Let's go back to this confidence interval that we did for the proportion of adults who run into something while on their phones. So if I go to stat, remember I'm not calculating anymore. Now I'm running tests. That was a one prop Z test. One prop Z test. Whoops, and I clicked two prop Z test. Stat, test, one prop Z test. So it wants to know what was, darn it, this is not a test. Man, I'm struggling here, guys. Sorry, stat, test. I'm not running tests. I'm making an interval. So I need to go down until I see one sample Z interval. Two sample, one prop Z int. Okay. I want a one proportion Z interval. And it says, okay, well, what was X? Oh, 170 people said they ran into something. What was N? How many people did you ask? Oh, I asked 738. And I wanted to be 95% confident. You'll notice they use 95% quite frequently. I hit enter and it spits out the interval for me, 0.19997 to 0.26073, which, yes, very, very close to the values that we found here by hand. So sorry about going back. I just wanted to show you how to use the calculator for a proportion interval as well as for a sample interval.